Welcome everybody to the Rocky Mountain Mathematical Physics Seminar. Our speaker today is Howy Jordan, and he will speak about basics of information theory.
Thank you, Marcus. Yeah, so my goal today is to introduce and motivate some of the basic definitions of information theory to set us up to look at quantum information theory in the near future. But for today, we'll just mainly focus on the classical case, but I'll make a few observations that will kind of set us up to think about the quantum case as things come up. But let's start with some random variable. So let x be a random variable, which I'll abbreviate RV. And let's suppose that it has a finite set of outcomes, and for convenience, I'll just let them all live in R. And for the most part, I'll focus on intuition building with the finite case, but a lot of this can be extended, and I'll make a few comments about extending it to the continuous case and certain points. So x is a random variable with some outcome space omega and some probability of each event in omega occurring, which I'll probably denote p sub omega for the most part. Okay. So our goal is to find a way to formalize the idea that we gain some information when we make an observation of some events. There's a few ways to think about this that are kind of equivalent. You can think you've gained some information, or you're measuring how surprised you are based on the event that comes out, or measuring the uncertainty of certain events, but not in the sense of, say, Heisenberg uncertainty, just the sense of knowing or not knowing what's going to happen. So I'm going to write down a few things that I think should be sort of obvious characteristics of any attempt we make to quantify information in this sense. And we'll see that the standard definition of information and entropy that you might have seen before kind of falls out naturally just from some basic axioms. So the goal is to capture some notion of information content of an event. And intuitively, there's a few things we'd like it to satisfy. Sort of this condition zero, I'll just call this condition zero. This information content should depend only on the probability. That's just a way of saying, right, I don't actually care about the semantics of what's going on. We're just caring about the general theoretical apparatus of transferring any kind of information, regardless of what that information is. So we'll say that the information should depend only on the probability of an event. Sometimes this is explicitly mentioned, sometimes it's just kind of taken for granted, but I'll mention it here since it is kind of important. Maybe depending on how you're thinking of information, that might not be the most obvious choice to make. But we'll say, let's say I'm going to denote some information function by I. I would like that information function to be decreasing in probability. It's a decreasing function of probability, I should say. So why does that make sense? Well, intuitively, the more likely an event is, the less surprised you are when that event happens, the less information might be needed to convey that that event has happened. And if an event is completely 100% guaranteed to happen, then there's not really any information there at all. You already knew it was going to happen. There's no change in information. So we'd like it to be a decreasing function of the probabilities. And we'd also like that if we have two independent events, their information should be, in a sense, independent. So the way I'll write this condition is that if I take the product of two probabilities, which would represent two mutually independent events occurring at the same time, that the information contained in the event with the probability given by the product of those two probabilities should just be the sum of the information contained in the two events themselves. So this is capturing that idea that if I have two independent events, their probability would be the product of their probabilities, and the information should just be the sum of the information from those two events. If they're independent, their information shouldn't be interacting in any way or anything like that. Maybe just a small note here. This here condition implies that, just like I said, if something is sure to happen, if it has probability 1, then it should have 0 information. Sometimes that's listed explicitly, sometimes it's not. But in particular, since we're decreasing in P together, those imply that my function is non-negative. Sometimes, again, that's listed as an explicit condition, sometimes it's not. Okay? So, my claim is that if I just want an information content function that just satisfies these conditions here, that there's really up to a constant multiple only one solution. So up to some constant, the only solution is actually given by the function, which takes the probability to log of 1 over that probability. And since I'm doing things since I'm saying it's going to happen up to a constant, and this is a log function, up to a constant is basically the same as saying up to some choice of base for my logarithm. Okay, so let me outline a quick proof that this should be the case. There's actually a few ways to show this, but I'm going to give a simple little analytic proof. So let's say I have some natural number, and actually, let me say I want a positive integer, so some element of z bigger than 0. And let's say I have some real number r, and let's say there's such that b, where I'm just going to fix some base for my logarithm for now, b to the minus r is greater than some probability that we're choosing to evaluate to the n, and bigger than b to the minus r plus 1. So what I'm saying here is if I represent this probability p in base b notation, like if b is 10, then I'm just representing it as a decimal number. I'm asking which values of r give me the most significant digit of my probability. So b to the minus r is where that very last 0 is. B to the minus r plus 1 would be where that very next number is. And my probability, or really my probability to the nth power for any n, I should be able to squeeze it in between, 0.001 and 0.0001 or whatever it happens to be. So let's say that I've given some probability I want to evaluate. I pick any n and I find the r such that this holds. Okay, then in that case, by just applying the conditions that we've laid out here, in particular condition 2, well, I'm also applying condition 1. Let me say H1. So if I were to apply condition 2 over and over again to 1 over b to the r, then I'm saying that I should get r times the information content of just something with probability 1 over b. Same thing over here, except r plus 1 times the information contained in an event with probability 1 over b. And in the middle here, I'm going to just say, well, I'm going to do this in 2 steps, actually. I only wrote 1 step down here, but let me write it as 2 steps. Okay, so first, just applying condition 2 to each of these little statements tells me, okay, well, I've got r times 1 over b, so I should have r times the information in 1 over b. I have p to the n, so I should m times the information in p, and so on. And since I'm asking for this function to be decreasing, my inequality is going to flip around like that. And for convenience, I'm going to go ahead and divide everything by this I 1 over b, and I'm also going to go ahead and divide everything through by this n here. I'm going to do that in 1 step. R over n, r over n plus 1 over n. And in the middle here, I've got my information content for p. I've divided my n away. I've also divided this I 1 over b away, but that constant doesn't depend on the n and the r I chose, right? That's just whatever base I fixed for my logarithm at the beginning. So I'm just going to say there's some constant multiple there that I don't really care about. That doesn't depend on r and n, which is important, but it's just some constancy. Okay? So in particular, this is a solution. This formula that I gave, log base b of 1 over p, hopefully it's not too hard for you to agree that that is at least one possible solution to this problem of giving an information content function. So to show that it's the only possible solution, I'm just going to subtract my arbitrary I that is some arbitrary solution to this. I'm going to subtract it from here and show that in the limit, the distance between those has to be 0, and that's not too bad. So in particular, right, the same inequality holds for I prime with some other potential constant there. But again, I don't really care about that constant. So this inequality holds for this particular solution, holds for any generic solution. So what does that tell me? That tells me that this C times I of P, my generic solution there, can only differ by my particular choice of solution by at most 1 over n, but n was an arbitrary positive integer, and these constants didn't depend on that at all. So in fact, I can say that as n goes to infinity, we see that my new function I is actually just some constant multiple, in this case C prime over C, but again, don't really care about that. I just care about noticing the fact that yes, any particular solution you try to give to this information content problem is necessarily just some log to some particular base. So that's kind of nice. Sometimes the presentations of this idea don't really give any justification for it. They just give a definition. They say the information content is log 1 over the probability, and let's move on. But I think it's nice to see that it really does follow from some pretty simple choices you would want to make for an information content function. So I think that's an important thing to consider. So that's what we'll call the information content. So the information content is exactly that function. Sometimes it's also called surprise or uncertainty, like I said, but I'll mainly just say information content. So of some event omega that has probability p sub omega is given by log of 1 over p sub omega. So sometimes I'll write that it's a function of the probability. Sometimes I'll abuse notation a bit and say that this is the information content of the event itself. But either way, I really just mean this formula log of 1 over the probability of that event. And I realize I was writing that omega as a subscript, not as an argument there. So let me do that. Okay. For the most part, I'm just going to write log over and over again. Like I said, up to a constant, there's only one option. Typically, the log I'm going to choose is going to be base 2 because that has a very nice connection to digital information processing and storage, and a lot of the examples I give are going to be in that vein. So for the most part, you see log base 2 done a lot, but for the theoretical work, it doesn't really matter. Okay. So just as some kind of quick examples, right? Maybe the simplest example you can think of is taking a fair coin with heads and tails as 2 options, each probability being just 1/2. What is the information if I'm measuring things in base 2? Well, in this case, the information content of each of these is 1 unit of information. Well, what should these units of information be? It's going to vary based on your choice of base for the log, but for log base 2, they're typically called bits. And the word bit actually originates with Claude Shannon's paper of Mathematical Theory of Communication, where he developed the foundations of all of these ideas. So the very first time the word bit ever appeared, at least in print that we know of, was at this moment when we introduced the information content function. Sometimes it might be convenient to use base 3 and talk about trits. Sometimes people do natural log and they call them nats. But for the most part, I'll just speak in terms of bits today. So for a very simple case with a fair coin, you gain 1 bit of information by realizing the event and getting the information about what happened. Let's do a slightly more interesting one that I'll bring up a couple of times. So now suppose that X is a random variable with the outcome space given by 4 letters, A, B, C, D. And I'll say that the respective probabilities of these are 1/2 for A, 1/4 for B, and 1/8 each for C and D. This is a pretty common example to see in this setting. So you might have seen this example before if you've done any research into this. Okay, so in this case, how much information do my 4 events, A, B, C, and D have? Well, A, like just with a fair coin flip, has 1 bit of information, but B has 2, and C and D each have 3 bits of information. So getting back to that idea of surprise or uncertainty, the idea is A is going to occur half the time. So when it occurs, we're not as surprised that it occurred. Yeah, we gain a little bit of information. We understand that A occurred, but we weren't too surprised. It happens half the time anyway. But B only occurs a quarter of the time. So we're sort of twice as surprised when B happens. And C and D only happen 1/8 of the time. And we're sort of 3 times as surprised when C or D occur. Sort of the intuition going on there. Okay. Another way to think about this, which I'll just mention while I'm raising this, you can also think of this information content as telling you how many questions you have to ask to uniquely specify an event. Really, I should say maximally informative questions. So if I'm asking a bunch of yes/no questions, like if we're playing 20 questions, and I want to specify one of these events with certainty, I can specify A with just 1 bit of information. You can just ask me, was it A or not A? But with B and C, I need a little bit more questions to uniquely specify that event. And we'll get a better idea of that in a second, but it's kind of a useful intuition to have as well. Okay, so that's the information content of some events. Usually we don't really deal with the information content itself very directly. Usually instead what we care about is the average information content, also called the entropy. Sometimes the Shannon entropy, if we want to distinguish between thermodynamic entropy and the von Neumann entropy that we'll see soon. So the entropy of a random variable X is the expected value, the expectation of that information content function I. Usually this entropy is denoted with an H, and sometimes we'll say H of X, even though it really just depends on the probability distribution of X. Again, I'll use notation a lot and say that it's a function of X. And maybe if you've done some probability, you've seen this notation before, the expected value of this function I. But in this case, since mostly what I'm considering are simple finite outcome cases, this is just the sum of the probabilities for each event in X. So maybe I'll say that my event space has some X1 through some finite number Xn, and each one has probability P1 through Pn. So I sum up over the probabilities times this information function, so log 1 over Pi. Just the average amount of information contained in this random variable. Maybe as a small remark, you do often see this presented this way, negative sum Pi log of Pi, right? Just using a basic log property. Really just a matter of taste. I prefer this first presentation, but then again, I also prefer thinking about information content first. A lot of sources just give you this definition like on page 1 and just go from there. But I think this definition at least is a little bit more intuitive in my opinion. Oh, and maybe a small caveat I should mention here. We do, by convention, decide that 0 times log of 0 should equal 0. I mean, simple limit tell you that that's probably what it should be anyway, but we'll make that an official convention here just for the sake of having a well-formed definition. Okay. So I want to make some observations about this notion of entropy here. First, if X has n outcomes, then this entropy is maximal in the case that this random variable X is uniformly distributed. So for instance, my fair coin flip 1/2 chance of each option, 2 options, it's uniformly distributed. You have the maximal amount of information, or of average information there. You have the maximal possible amount of surprise or what have you. Maybe just as a quick sketch, it might be helpful to see what this entropy function looks like as a function of the probability of some 2 event space. So I'm just going to say, like, let's pretend that X has 2 outcomes. Outcome 1 happens with probability P, outcome 2 with probability 1 minus P. What does this entropy look like as a function of that choice of probabilities? It's a nice little curve like this, with the maximum happening right here at 1/2. But just to give you a kind of a rough idea for how this entropy function works. So like we said, if something occurs with 100% probability, or dually, if it's the other option that occurs with 0% probability, then we don't have any information. We already knew what was going to happen. And if the events occur with equal likelihood, then we have the maximal possible amount of information, which in this case, if I'm doing log base 2, is 1 bit. Okay. Another observation that's worth making here, which you can see from the graph I've drawn, but you can obviously need to prove it more formally for more general situations, but it does hold that this function h is always a concave function. What do I mean by a concave function? I mean that if I were to evaluate this entropy on, say, a new distribution that I construct from my other distribution. I wrote this, well, we'll just write it that way, that's fine. So maybe P and Q are 2 different probabilities of 2 events holding, and I take this convex combination of P and Q. Well, if it was convex, I would have it less or equal to, this is concave, I have it greater or equal to lambda times the information content in P plus 1 minus lambda the entropy of Q. I point this out because this also has a nice kind of intuitive justification. What am I saying here? Well, let's say that I had maybe 2 coins that I was flipping, and neither of them are fair coins. Maybe one coin is heads with probability P, and the other is heads with probability Q. And I'm going to pick these coins randomly, picking maybe coin 1 with probability lambda, and coin 2 with probability 1 minus lambda. And in that case, I choose a coin randomly, and then maybe I communicate the result of that to someone else. How much information did they gain? Well, this inequality is telling me that they should gain at least as much information as the average information they would have gained from just individually choosing the coins and flipping them themselves. But in general, they can gain more information because they also gain some information about my random choice of coin. But they definitely shouldn't gain less. They should gain at least as much information as they would have gained themselves on average by doing these 2 coin flips. Okay. So let me use this example here again. Let's say that we have a random variable with 4 outcomes, A, B, C, D, with the probabilities 1/2, 1/4, 1/8, and 1/8, like I had up there before. What is the entropy in this case? Not too hard to calculate. Right, it's going to be 1/2 times 1 bit of information, 1/4 of 2 bits, and 1/8 of 3 bits, and 1/8 of 3 bits. Which just comes to 7/4 bits of information. So on average, I need a little less than 2 bits of information to capture this random variable here. And observe that if X was uniform, this would be 2 bits. So this is a little bit less. If it was uniform, it would be 2 bits. We ended up with a little bit less information needed because we have a little bit less, maybe saying less randomness isn't quite the right way to say it, but we have a little bit more predictability in the outcomes than we do if it's truly uniform. Okay, so from here I want to move towards talking about encoding information, especially encoding it for transmission in some way. So what does it mean for us to encode some information? Well, yeah, let me go ahead and do it this way. I'm going to change the way I wrote this in my notes a little bit. Okay, so let's say that we have two alphabets, so to say, of information. So I'll write omega 1 and omega 2, and these are just, some event space for some discrete random variable. But I'm going to think of them like they're alphabets that I'm wanting to use to encode, especially using this second alphabet to encode things about this first alphabet. Okay. So by an encoding, what I mean is that I have a function that takes in some element of my initial alphabet and gives me not necessarily a single element of my output alphabet here, but some finite string of things from that alphabet. So that's what I mean by this upper star notation, also called the clean star, if you've seen that before. It just means that I'm taking the union of all finite strings. So this contains every single possible finite string. So an encoding is a function, which I'll usually call C, that takes my original events and assigns them some string of characters from some other alphabet. We'll also talk about the extension of the encoding. And this is just the induced function on finite strings from my first alphabet. So if I can turn each character into a finite string, then I can turn each finite string into a finite string. And I'll just use a C upper star to denote the extension of a particular encoding that I've chosen. Okay? So this is what I formally mean by an encoding. And what kind of properties might an encoding have? Well, that's probably okay if I write this a little bit so I can write these here. So we'll say that that encoding is non-singular if the original function C is an injection or is monic. I'll write monic for short. We'll say that it's uniquely decodable if the extension is monic. And a couple other properties I want to consider, really just one more. This property of being instantaneous. So non-singular coding, I don't assign any two characters in my alphabet to the same finite string. Okay, that seems like an obvious thing we want an encoding to do. Uniquely decodable, I don't ever accidentally have two different finite strings of characters that are mapped to the same finite string. And the other property that we're interested in is this property of being an instantaneously decodable code, also called prefix free. Instantaneous or prefix free if and only if for, how should I say this? For no character in my, let me say it this way. For no two characters in my original alphabet, do we have that one is a prefix of the other, and one coding is a prefix of the other, excuse me. So what do I mean by prefix? I just mean that one of these is the same finite string, but with a few extra characters at the end. It's the prefix of C. So my code will be instantaneous or prefix free if I never take two characters and put one to the first chunk of a string that I'm assigning a different one to. Okay. So let me give some examples of all of these. And I'm going to use my A, B, C, D example just like before. Let's say I'm trying to encode A, B, C, and D. And let's say that I'm trying to encode them in just a two-character alphabet, say just zeros and ones. Okay. Well, okay, a singular code, that'd be easy to write down. I could just assign everything the same 0 or 1. So I'm not going to give an example of that. But let's give an example of a code that's non-singular, but it's also not uniquely decodable. Not uniquely decodable. So for instance, I could assign the character A1, and I could assign B01, and I could assign C10, and I could assign D11. Just a choice of encoding. Well, this is non-singular because I didn't assign any of my characters to the same string, but it's not uniquely decodable because, for instance, if I look at the code 001010, you can't tell me if that's A, C, C, or if that's A, B, B, A. Both of those finite strings get mapped under the induced extension function to this same finite string here. So there's an example where we're non-singular, but we're still not uniquely decodable. Definitely don't want that to happen. What about one that's uniquely decodable, but it's not instantaneously decodable? What does that look like? Well, for instance, I could assign A to 10, B to 00, C to 11, and D to 110. So we can already see this fails to be prefix free because C is a prefix of D. So what's our intuition for this word instantaneously decodable? Well, if I'm sending you bits and I send you a 1 and then I send you another 1, you have to wait for the next bit to see if I've already sent you a C or if I was actually planning on sending you a D. And for one that is instantaneous, that is prefix free, we can do 0, 10, 110, and 111. Now I'm not only uniquely decodable, but I'm also instantaneous. Anytime you get a 0, you know you just received a 1. Anytime you get, or sorry, you know you received an A. Anytime you get a 1 followed by a 0, you know it was a B. If it's 2 1s and a 0, you know it's a C. If it's 3 1s, you know it's a D. You always know that as soon as that code finishes, you don't have to wait for the next characters to make sure that you decoded it properly. Okay. So yeah, I don't want to write that again. Let me just mention it. Okay. So let's say that I wanted to encode the information that's occurring according to this probability distribution on 4 letters that I put up here at the top right. Okay. My claim is that this last code here is actually the optimal choice for this particular arrangement. Now, one thing that's worth noting here is that I only had 4 characters, so if I wanted to uniformly encode them, I could just go with 00, 01, 10, and 11. That would be a instantaneously decodable, uniquely decodable, non-singular, everything we want. But why is this option, where in particular I'm using 3 bits for C and D, more optimal than just assigning everything 2 bits? Well, if you think about the entropy calculation I did over here, you'll see that this is also equivalently the length of each of those strings that I just gave over there. And this entropy is equivalently calculating the average length of that particular code choice that I made. And that average length is 7/4 bits. So if I have these symbols occurring according to this probability, I will use less bits on average if I choose this encoding I just gave versus just giving them all 2 bits of symbols to encode with. But we want to make that a little bit more precise and actually prove it. And we also might have the question, well, can we do even better than that? If I know I have this distribution with entropy 7/4 bits, and okay, I have one encoding that does 7/4 bits, or 7/4 bits of length per encoding. Do we know that that's necessarily the optimal choice, or can we do better? It turns out we can't do better. That is, in fact, the best we can do. And that statement is the content of Shannon's original noiseless encoding theorem, or sometimes the source coding theorem. So That's one important thing that this entropy is telling us. It's telling us the very best we could ever hope to do for encoding the information occurring according to this distribution. The most efficient we could ever possibly be. Yeah, let me do this. So before I actually write down the noiseless coding theorem, maybe I'll just mention this other theorem that really the noiseless encoding theorem is a corollary of, so this is sort of more important. So if I have some code C, and maybe I'm encoding, let's say, N symbols into strings built from M symbols. So my omega-1 has size N, my omega-2 has size M. So if I'm building a code that way, and let's say that the lengths of each of the codes that I assign to each of my original N symbols are, I'll just say L1 through Ln, where maybe X1 through Xn are the actual original alphabet that I'm using, or A1 through AN probably is better. If this code C is prefix free, if it's an instantaneous code, then we can show that the sum of M to the minus Li, so I take the M symbols I'm building, I take each one to, well, 1 over M to the length of each of these codes and add it all up. But that's always going to be less than or equal to 1. And the converse is true. I won't write the converse out, but if you give me N choices of lengths of code that satisfy this property, I will always be able to build a prefix-free code out of it. What time am I looking at? Okay, yeah, I'm not going to go through the proof of this, but it's actually not too hard to see. You just imagine starting with a tree with M branches at each node, representing all the possible strings you could make, and just kind of do a little bit of combinatorics from there. And it's pretty easy to see that actually this inequality holds. And once we have that inequality, we can prove Shannon's noiseless encoding theorem, which tells us that yes, in fact, that entropy does give us the best possible efficiency for an encoding. So let me sketch out the statement of Shannon's noiseless coding theorem without maybe writing it in its full gory detail. We'll just say that the expected length of a prefix-free code, so I'll use L to be this expected length. I literally mean like the average length of a prefix-free code. And we'll say it's an M-ary code, meaning that I have M symbols that I'm encoding into of some random variable X, is bound by, well, the lower bound is given by the log base M entropy. So I'm just going to write H sub M to mean, okay, I'm choosing M as my base. But again, usually this is a 2. And usually we're encoding things in binary strings. So that entropy gives me a lower bound, a strict lower bound on, or sorry, a non-strict lower bound, an obtainable lower bound on the average expected length of a prefix-free code. So just like we saw before, I had 74 bits of entropy in this situation here, and I was able to find a code that did in fact average 7/4 bits per symbol. And it also, even better, can give us an upper bound with the condition that we look for an optimal code. So maybe I should write that as a separate statement. So let me say if C is optimal in the sense that I'm taking infimums or I'm taking lower bounds over the possible encodings, then that code also has an upper bound given by that entropy plus 1. So the entropy and one more bit than the entropy form a nice bound on the best possible coding you could ever give for any particular random variable, random source of data or information. Okay, so let me skip that. Okay. So let me make a comment real quick about some things that are a little bit odd here compared to what we would expect to happen in the quantum realm. Just as sort of a quick observation. If, for instance, let's say I have a pure state on C2. So I'm going to call this state psi, but let's say that I'm writing it in a nice standard basis where my two basis elements represent being spin up and spin down, and each one of these has a coefficient lambda1 and lambda2, subject to the usual condition that, well, I'll just write it, lambda1 star lambda1 plus lambda2 star lambda2 should equal 1, right? So I'm taking something from the unit sphere, using those as my coefficients. This is a pure state. So if this is a pure state, this classical entropy that we've given thinks that, and I won't write out this calculation, but it thinks that we have non-zero information. So according to classical entropy, even a pure quantum state can have non-zero information. For instance, if both of these are just root 2 over 2, root 2 over 2, each one of them has half of 50% chance of occurring at half a spin up, half chance spin down, then classically it seems like I gain 1 bit of information every time I do a measurement. But that's a little bit strange. In the classical case, if we ever have a pure state, we know 100% what's going to happen and we have no information. Here we're saying we can have a pure state and still have some non-zero information, at least from the classical perspective. But from a quantum mechanical perspective, we shouldn't actually have any information here, at least no quantum information. We already have a pure state. We already know what pure state it's in. There shouldn't actually be any information. And in particular, we would have the same amount of information from this pure state as we'd have from a mixed state that was 50% chance of being in a certified spin up state and 50% chance of being in like a certified spin down state. Okay, the statistics of just that one state look the same. So our classical entropy thinks that this pure state and this mixed state have the exact same amount of information in it, which is a little bit odd and unintuitive when we think about what a pure state should be. And so there's a motivation there to want to consider a different notion of entropy, which we'll see next week when Daniel tells us about it. But just wanted to point that out there, that there is something that's sort of different here about classical information versus the quantum information. Okay. So there's some other notions of entropy that I want to mention and define. By the way, stop if you have any questions, or stop me if you have any questions.
I have a question.
Yes.
So in this theorem, expected length, the prefix for the American code of a random variable. So what is it? What is the code? Is there a code associated to a random variable?
Yeah. So this random variable x, for instance, you could, this random variable x might have like A, B, C, and D as its 4 possible observations we can make, the 4 possible events. You want to think of this as being like a source of information. Like this X could be a person emailing you from across the country, and they have a half chance of sending you an A and a quarter chance of sending you a B. And obviously I'm being a little bit obtuse here, but hopefully from there you can extrapolate how to make a more realistic scenario. But yeah, this random variable should be thought of as the source of some string of characters. If I was being a little bit more precise here, I would have written up that I had a sequence of random variables which were independent and identically distributed according to the distribution of this variable x, and therefore all have the same entropy as x, and we want to encode the strings resulting from measuring this sequence of random variables. That's a more precise statement. Does that clarify?
I guess I still don't understand, because the outcomes of X in your example are like A, B, C, D.
Yeah.
So what is the encoding of those things into the new alphabet? Like, 'cause
it would be a choice of every event being assigned some string of characters in some completely different alphabet, say just zeros and ones. So my encoding I gave before, where I assigned A to 0, B to 1, 0, and then 1, 1, 0, and 1, 1, 1 for C and D. If X has the outputs A, B, C, and D for the observations that my friend over on the other side of the country is making, then maybe they want to send me not actually A, B, C, and D. They want to send me a 0 or a 1, 0 or a 1, 1, 0 or something like that. Does that make sense?
I see. So I guess the way you wrote it kind of seemed like there was some sort of canonical way to associate to each random variable some code.
No. The expected length of a prefix-free memory code of the random variable. Any prefix-free memory code you pick. So maybe I should say any prefix-free memory code.
X from some sigma algebra to omega 1, and then
yes.
we're post-composing with some other code.
Yes, yes, exactly. Yes. Okay. Any other questions? Hearing none, I move on. Okay. So in general, we care not just about the observation of a single random variable. We usually have a couple random variables related in some way. So just like we have notions of joint and conditional probability, we have notions of joint and conditional and so on entropy. So the joint entropy of two random variables now, X and Y, is not really a new definition, but I'll present it like it's a new definition. It's actually just the entropy of the joint distribution of X and Y. So sum of the probability of X and Y occurring, Xi and Yi occurring together, and multiplied by log 1 over that probability. So this isn't really a new definition, but this notation is new and it's used a lot. So this is telling you just the entropy of this joint distribution. And we can also define conditional entropy, right? We have conditional probability. What's the probability of observing some output X from the random variable X if we already know something about the random variable Y, say? And it's denoted with similar notation to the conditional probability you've seen before. So I guess this is backwards from what I just said out loud. This would be the conditional entropy of Y given X, not X given Y. That's just defined to be the expected value of the conditional probability. So most of these kind of definitions are just sort of falling out from the same definition you have in probability. But we do get, of course, some nice interesting properties that we care about. So one I'll mention here, that joint entropy of two random variables is always the information in X, the entropy of just X, plus the entropy of Y given X. So we can always break down the joint entropy into the entropy of one variable plus the conditional entropy of the other. And as a corollary, we have that the conditional entropy, and this is probably what's more interesting from an intuitive standpoint, the conditional entropy of, say, X given Y is always strictly, well, not strictly, is always less or equal to the information of X. So what does that tell us? Well, if we have some extra information about X, say in the form of some other random variable Y that we're able to talk about conditional probabilities with respect to, then in general, we should be a little bit less surprised about the outcome of X than we would if we didn't have the information coming from Y at all. From there, we also like, yeah, this will be the last one. Well, these next two are essentially the same. So from there, we also have a notion of mutual information and divergence between two information sources, also called relative entropy. So yeah, let's just do this. Okay. So the relative entropy, and I'm going to start doing some abbreviations because I'm shorter on time now. The relative entropy, this is going to capture the idea of the information we, how should I say this? It's going to capture the idea of us incorrectly having some information by making an incorrect assumption about the probability distribution. So the relative entropy of two probability distributions, which might be coming from two random, well, not two random variables, they might be coming from some random variable, but we don't actually know the correct distribution. So let's say P and Q are two probability distributions. This relative entropy, also called the Kullback-Leibler distance or divergence, but it's not really a distance, it's not really a metric. So maybe divergence is a better term, or relative entropy. This is the expected value relative to the distribution P, which we assume is the actual correct distribution of log P over Q. So this relative entropy is somehow quantifying how incorrect we are when we assume that the distribution Q holds, but actually the distribution P holds. So for instance, maybe let me just throw these observations up there. If there is some element in our event space that has a non-zero probability of occurring, but which we've assumed has a 0 probability of occurring, then really just based on those conventions we made earlier about defining 0 log 0 and such, in that case, we have infinite relative entropy. So if we assume something can't happen and it can, then we're sort of as far off as you could possibly be. And this relative entropy is 0 if and only if P and Q are equal. So if this is 0, then we were spot on. We knew the actual distribution. If it's infinite, then not only was our distribution wrong, but even our assumptions about what could and couldn't happen, what was possible, was wrong too. Yeah, I won't throw up a calculation up here, but just as an example of what this quantity actually tells you practically, if you were doing, say, an encoding, if you assumed that your source had probability distribution P, but you encoded it as if it had probability distribution Q, then this relative entropy will tell you on average how much extra bits you're using that you didn't actually need to use because you made the wrong choice of distribution. And yeah, the last thing I'll give is this definition here of mutual information. I won't write out the entire thing. I'll just say what some of the symbols mean. So we sometimes write I, X, semicolon Y. I've seen that in a lot of sources. You also see it written as X colon Y, and I don't really know if there's a preference one way or the other. I was looking at a couple different sources and I saw both of these notations in there, so I'll mention them both. But we define this mutual information to be that relative entropy of the joint distribution of two variables X and Y relative to their product distribution. So this is telling us if the actual distribution of these pair of random variables X and Y is P of X, Y, that's their actual joint distribution. This entropy is telling us how far off we would be if we assumed that they were actually independent random variables and that they just had a product distribution. So maybe just as a quick proposition to show you what this information kind of tells you, you can show that it's equal to the entropy of one random variable X minus the conditional entropy. So in a sense, it's kind of telling you the reduction in uncertainty of X due to knowing something about the uncertainty of Y, or knowing something about Y. I'll stop writing things here. The last thing I'll mention is that from here, we now have enough apparati, I don't know what the plural of that is. We now have enough mathematical tools to think about not just noiseless encoding that I mentioned before, but an idea of there being some amount of noise in your communication channel in the form of there being some additional probability distribution, which can, say, give you a chance of receiving the wrong signal or receiving a different character than what you wanted, while using these notions of relative entropy and mutual information, we could state Shannon's noisy coding theorem and see that, in fact, we do still have some nice bounds we can place on our ability to transmit information over noisy channels. But I won't actually write any of that up. Just to say that hopefully just giving you these tools in the form of entropies for multiple random variables kind of sets you up to be able to do it. So I'll just stop there and go for any other questions.
Thank you very much. Any questions?
When you say the relative expectation, what is that? Expectation, so.
Yeah, so if I was going to write that out, and let me just erase what I've written here because these observations were nice, but we don't need it right now. So what I mean is I'm adding up the probabilities, I'm averaging the probabilities with respect to P because it's the actual distribution. So the actual average is relative to this distribution P. Yeah. Any other questions?
Okay, so let's thank the speaker again. And well, we will have next week a seminar talk by Daniel Spiegel on the von Neumann entropy. Thank you.
By the way, fun fact,